So, welcome to MAE 37E Mechatronics. I am Dr. Benfinio. I am a visiting lecturer here in the Sibley School of Mechanical and Aerospace Engineering. I have taught this course 3 times now. This will be the 4th since 2018. I also teach an online version of the class that we developed for Cornell, but I have not taught in person here since 2021, so I'm guessing most of you have no idea who I am. So I'm just going to start by briefly introducing myself before I talk a little more about what we are going to do in the class. So I live here in Ithaca with my wife, Dr. Erin Henry, who teaches in the shelter medicine program at the vet school. They provide all the animal care for the Tompkins County SPCA, in case any of you have ever volunteered there. Our 2 kids, Natalie, age 8, and Josh, age 4, who does not like holding still for pictures. The toddlers are exhausting, so if I ever look really tired, he is probably why. We also have our dog, Riley, and our cat, Trouble Fuzzy Bottom, who is what happens when you are a 4-year-old named a cat. I got my PhD in the Harvard Microrobotics Lab working on the RoboBee project, graduated from there in 2012. Left academia completely for a while to work in kids science education, so think of me kind of like Bill Nye, but not famous. Doing fun things like putting googly eyes on robots for a nonprofit called Science Buddies, which some of you may have heard of if you were into science fairs as a kid, and also some more kind of advanced high school level stuff, getting more similar to what you're going to be doing in this class. So, enough about me. Let's talk about this class. What is mechatronics and why should you care? So most of you are mechanical engineers. We do get some cross-enrollment from other departments. I am a mechanical engineer by training. My undergraduate degree is in mechanical engineering. So the perspective from which I teach this class and address a lot of the topics is really from the MAE perspective and kind of geared towards that understanding. So mechanical engineering as a profession really has its roots in the Industrial Revolution, right? Steam engines, things that at the time were exploding a lot. And people got together and said, hey, we should probably have some standards around how these things are built so they don't keep blowing up. And that's how ASME was born as a professional organization. Okay, fast forward 150 years, give or take, most modern systems that engineers work on now are electromechanical. Okay, so all the classic stuff, planes, trains, automobiles, boats, things that mechanical engineers worked on and developed throughout the 1900s kind of gradually got more and more electronics and controllers integrated into them until today we have super complex electromechanical systems like this. So my pitch to you on day 1, and what I will try to remind you of as we go through the class, is that even if you have no interest in this stuff as a mechanical engineer and you're kind of rolling your eyes like, if I wanted to have to learn circuits, I would have done electrical, like don't want to have to do this, is even if you are not the one designing the circuits or writing the code, you are probably going to have to work with the people who are. And you need to at least understand their language, right? You're not the one designing the circuit, but you're the one strapping it to a rocket to send it to Mars, okay? You're not the one writing the software to control the motors, but you're the one designing the arm that the motors are connected to, okay? So that's kind of the case in a big organization like NASA or a large company, and those are your own project teams here, kind of having, I'm not involved with project teams, but you have sub-teams where you may kind of be familiar with that structure. Or you can wind up in a much smaller environment, say like a startup or a grad school robotics lab, where things are a lot more interdisciplinary and the lines between mechanical and electrical engineering, robotics, computer science all get very blurry, and you do actually wind up doing a lot of this work yourself. So I'll try to come back to that as we get to kind of different topics throughout the semester to remind you why it may be relevant to you as a mechanical engineer. Okay, so what are we going to actually do in the class? Out of curiosity, raise your hand if you have seen the robot competition in Duffield at the end of a previous semester. Okay, so maybe half-ish of you, a little less. So if you haven't actually seen the competition, you may have seen these photos plastered all over the TVs in Upson. These are kind of the department's favorite PR photos because they show smiling, excited students. Many of you probably know Dave Partino by now, I'm guessing, who clearly gets very enthusiastic cheering for students in this. So for those of you who haven't seen the competition, we have a little highlight reel from a previous year. This is just kind of a 1-minute overview. The sound is on? Great. So I forgot that they edited this with the jazzy music, but there's Kirby, who I think most of you had last semester. So I like to describe this competition as BattleBots, but less violent. Okay, your goal is not to destroy the other robot. It's this little arena, and I'll talk about this more at the end of the day today, with these little cubes, and there is some objective with kind of arranging or pushing the cubes around within a 1 minute time period. There's me when I had more hair. This is videos from 2019. We do this in kind of a tournament style, so students compete against each other. The winner of the student tournament then faces off against a robot brought by ASML, which is a company that sponsors this class. See there the ASML logo on the shirt. You'll be kind of hearing more about them throughout the semester. And then they bring a robot every year, and the student winner faces off against them. I have not been keeping track of the wins and losses. I think the students had a pretty bad losing streak for a while, but then maybe in the early 2020s we kind of came back and upset them. So I don't remember how it's gone the last couple of years, but going to win that competition. So that is the end goal. That is the fun thing at the end of the semester. How do we get there? Okay, what are the topics we're actually going to cover in the class? So we're going to start out with circuits, and initially some very basic things that you should remember from physics, which is a prerequisite for this class. Okay, there is an additional homework assignment that's kind of going to be, hopefully, dust off the cobwebs from if you took physics last year or last semester. But then we're going to get into some more advanced stuff that you usually don't see in an intro physics class. So introducing things like diodes, transistors, operational amplifiers. If these diagrams just look like squiggles and mean nothing to you, don't worry about it. It'll make sense by the end of the semester. Combining resistors and capacitors, which you should have seen before, to build filters. So kind of a bunch of new circuit topics. But then the difference between this class and a pure circuits or pure physics class is we're now connecting stuff to a microcontroller, right? So we are interfacing code with the circuits to control them. And you're going to learn about all the little bits and pieces and sensors and things that you can kind of actually do interesting stuff with circuits instead of just doing math with Ohm's law, right? You're going to learn how to read data sheets, so you have some part with 16 pins. Where do you connect which wires? What do the pins do? What are the maximum voltage ratings so you don't accidentally burn the thing? Where do you buy all of this stuff? I'm guessing most of the Mechies are probably familiar with McMaster-Carr by now. Okay, so think of DigiKey kind of like McMaster, but for electronics, right? So you all will get, again, I'll talk more about this later, but you get a budget for extra parts for your robot at the end of the semester. So if you want to buy an extra motor or something, kind of weeding through and deciding how to do that. We are going to learn instrumentation, which again, most of you should have taken system dynamics last semester. This used to be flipped. Mechatronics used to be offered first in the fall. So in theory, all should have used an oscilloscope before. In my experience, people kind of treat the oscilloscope like this scary thing with lots of buttons and knobs that you don't want to touch. One of my objectives in this course is to have the oscilloscope be your friend. It's something that you are not afraid of, and think of it as a useful tool to visualize what is going on in circuits. So again, thinking of this as a mechanical engineer, I think the problem we usually run into is that Newtonian physics is intuitive to us, right? We throw something up, it comes back down. I push something, it moves. Okay? Electricity is not. It is literally all around us, like in the walls in this room, surrounding us, but you can't see the individual electrons moving around. And as a human, if you can feel electricity, that's usually bad, right? So as opposed to kind of forces and motion and things that make sense to us at the time and distance scales that we experience the universe as humans, you can stare at a circuit, like there's a circuit inside this little clicker I'm holding, right? But I can't see what's happening. So the oscilloscope is very useful for kind of visualizing what's happening when you're trying to get your robot working for the competition and it's not working and you have no idea why because you're just staring at it, but it's not visibly broken, right? So we're going to come back to that a lot this semester. Using the Arduino, which again, I'll talk more about this later. Some of you, out of curiosity, raise your hand if you have used an Arduino for something before. Okay, so again, maybe roughly half the class. We're probably going to go a little more under the hood than what you've done previously, particularly when it comes to kind of the functionalities of all the different pins and the code. And again, don't panic if you've never seen this before. We'll talk more about this later. You know, if you have used it, this code over here on the left probably looks familiar to you. If you haven't, just glancing at it, you see how basically this is a nice human readable language with English command words, right? So even if you haven't seen the language, you can probably look at this and start to think, digital write high, digital write low. Okay, I'm turning something on and off with this code, right? So this is the code to blink an LED. It's kind of just literally just flashing a little LED on and off. It's kind of the hello world equivalent with circuits and microcontrollers. In this class, we're going to be learning to code in binary with something called registers. So these are kind of individual memory locations in a microcontroller. And there are kind of some advantages and neat things about learning to do it like this, even though it is harder. People kind of grumble about it first. We're not going to get to this later in the semester, but I'll kind of come back to the motivation for learning to do everything that way. A couple of things I want to let you know about kind of the recent history of this class and things that have changed. I guess so were you guys in like late middle school or early high school when the pandemic hit? You weren't at Cornell yet, right? I'm getting old, so it all just kind of blurs together for me now. So March 2020, this class was taught in the fall. When we were preparing for it, we didn't know if we were going to be able to do anything in person at all, right? If we would be able to do, have to be fully remote. So we explored a really neat online circuit and Arduino simulator that lets you both build a circuit and run the code side by side in a single browser window in preparation for having to go fully virtual, which thankfully we didn't have to do. I'll talk about that more in a second. But even after the pandemic kind of ended and everything came back to in person, we realized that this is a really great teaching tool because these tiny little lecture hall desks, it is way too crowded in here to actually kind of prototype circuits, but you can bring laptops and follow along with me as I do this, which I find to be way more useful than just watching me write code on a projector. Okay, I don't think learning to program like that is very useful, so we will still be using this. It's not a replacement for in-person, hands-on physically building the things, but this is going to be a useful lecture tool and for some things like pre-lab assignments. We are also, another major change, you are all going to get individual circuit kits. Okay, so we are not replacing group labs in a group project, but the problem we had with this class historically, again using the oscilloscope as an example, is that students would divide and conquer tasks into labs. And if there's one person in your group who already knew how to use an oscilloscope, great, you're the oscilloscope person because that lets us get this done quickly and get out of here. And I 100% do not blame students for doing that because I did the exact same thing as an undergrad, right? Your goal is just to get the lab done as quickly and efficiently as possible. So my lab partner and I divided tasks. She looked at the data sheets and picked out all the right parts and handed them to me, and I put them in the breadboard. We just did that for the whole semester. The problem is if you do that, then one or two people in the lab group never learn to use the oscilloscope, right? So you are all going to get, right here, a little pocket-sized oscilloscope that is smaller than your phone, a multimeter, breadboard, LEDs, resistors, all that stuff. So you individually learn all of these skills and don't somehow get through the entire class without learning something. But again, this is not a replacement for group projects. There are still going to be group labs, and the final project is done in groups, but this is to make sure you all kind of go into the final project having a more even exposure to those skills. Okay. I want to clarify what this class is not, again, because we have cross-enrollment from other departments and some people may not have taken the MAE curriculum coming into it. So this is not a mechanical design class. Again, most of the sophomores, and it used to be called mechanical synthesis, it's called mechanical design now. So I'm not sure which version everybody took, but we're not doing gears, pulleys, 3D printing, machine shop, all that kind of stuff was covered at the sophomore level for the MECs. And we're not getting really deep into kind of full-blown upper-level circuit analysis. Like you're not going to finish this class and pop the case off your computer and understand how the motherboard works. Okay, we're looking at kind of those screenshots I showed earlier of smaller, simple circuits with 3, 4, maybe half a dozen components or something, but not, this is 4,000 level ACE territory, so we're not going there. Okay, so another thing I want to talk about briefly is the difference between mechatronics and robotics, because interestingly, you will get different answers if you ask different people this question. There is a paper linked in the lecture slides, which I'll post after this, where they actually surveyed people in industry, people in academia, and students, and all three groups gave different answers as to whether mechatronics is part of robotics or vice versa. I will give you my take as far as this class and the Cornell curriculum is concerned, in case you're looking at it and going, well, the end project is a robot competition, why isn't this called robotics instead of mechatronics? When people talk about robotics, I think of higher level things like human-robot interaction, artificial intelligence, navigation, mapping, kind of higher level computational things. Clearly, robots also includes dynamics and mechanism design and all that kind of lower level stuff. But I view mechatronics and what we're teaching in this course more as that lower level hardware interaction and interacting with sensors and motors. Not, I'm going to build something to map out and drive around the hallways of this building, right? That's autonomous mobile robots, which is one of the 4,000 level MECE electives you can go take, which is usually a again, used to be taught by Professor Hadas Kreskazine. I'm not sure who's teaching it now, but it's kind of a popular follow-up to this class. Pardon me. So, kind of looking at a map of classes and how we're connecting them all here. Again, most of you should have taken an intro programming class. Used to be either, so out of curiosity, how many of you took the MATLAB version? Okay, so I think they have switched this over, so freshmen now are all taking Python, but I guess that lag there, so we still have people who have taken MATLAB, some who have taken Python. All of our programming is going to be in C, which you may or may not have seen before, but once you know how if statements work in one language, it's kind of just a matter of learning where the parentheses go in the next language, right? So don't be afraid if you haven't learned C before. You should have taken the intro physics course, which also talks about electromagnetic waves and spectrum and all that. Ohm's law, resistors, that kind of stuff should be familiar. You should have taken mechanical design. So in this class, again, we're connecting all of this stuff with a microcontroller. Okay, so using a program to control the circuit, which is then connected to a motor and interfacing with the mechanical system. This is kind of very broad, right? So if there is a specific thing you're more interested in here, there are other classes you can go take that are going to go deeper than we have time to do in this class. So you've got an entire programming class on C, an entire 4,000 level ECE course on microcontrollers, 2 other full-blown circuits courses, which again, most of the Mechis probably aren't also going to take those because you're taking Mechatronics to fulfill your circuits requirement. And then, again, various 4,000, 5,000 level MAE electives like autonomous mobile robots. So that's kind of the, I might not have all the course titles perfectly updated here and everything, but that's kind of the general idea. Okay. That was a fire hose of information in the first 15 minutes. Any questions so far kind of on high level stuff and like what we're covering in the class or what the class is or isn't? Thought I saw a hand over here, but I think you were just adjusting your hair. Okay, we're good. Okay, let me remember, all right, switching gears a bit. I want to take a minute to talk about mental health because this is something that means a lot to me personally and clearly Cornell kind of has a fraught history with in terms of, so I joke about it, but it means a lot to me in terms of removing the stigma around talking about it and getting help, right? So here's the deal. At this point, especially with the pandemic, like half the people in this room have been to therapy, okay, myself included. And I can stand here and I see some nods, thank you. I can stand here and say that in front of almost 200 people, like who cares? Okay? There's nothing to like be ashamed of. So if this is something where, I hear students be like, oh, I hear there's a really long wait time, or I know somebody who didn't like their therapist, or I don't want people to know I'm in therapy, like trust me, take it from someone who has been there, just make that first appointment. It is worth going. Okay, this is all with the caveat that I'm not a mental health professional, so this doesn't mean like my office hours or a therapy session, but I find that it kind of makes it easier for everyone in this course, so you, the TAs, and me, if we all kind of take a collective deep breath and ratchet down the stress level, because I know Cornell students have a tendency to kind of get a little high-strung about things. I am here to support you and help you succeed in this class. I don't want to make your life more difficult than it needs to be. That does not mean I just make it easy and give you all A's. Okay, this class is rigorous, it is difficult, I have an obligation to teach you the material, but I think I can do that in a supportive manner. I also find that it is helpful if there's kind of a ground-up or student-led approach to this and not just top-down, like what you're getting from your professors or the administration. So be honest, raise your hand if you have ever been on either side of this conversation. I see some smirks, raise your hands, be honest, come on, okay. So I did not make this up. I literally overheard this the first week I was teaching here between 2 of my TAs, and it kind of caught me off guard. It was like my answer would have been like, it was nice I went to the beach, I don't know. So please don't do this to each other, okay? Clearly like addressing the whole culture around project teams and internships and clubs and all of that is like way bigger than just this one course or me as a visiting lecturer, but I figure it can't hurt to start somewhere. So kind of, again, take a deep breath, think of each other as collaborators and kind of potential future coworkers, that sort of thing. You're not all in this in like a bloodthirsty competition against each other. Again, just kind of deep breath, ratchet down the stress level. I also kind of like to attempt to address this self-perpetuating myth among students that to get a job, you need to do a million things for your resume, right? I think this kind of carries over from like, clearly you all got into Cornell, you were very successful in high school, a lot of people did a lot of extracurriculars to kind of build your college application. That's not how it works for getting a job. Finally, and then we'll kind of get back on track for some of the more boring course logistics stuff. You all saw like half the people in here-ish raised their hands about having used an Arduino before, and I'll explain this graph in a minute. This is something people get kind of worried about, like, oh, I'm going to be at a disadvantage. Like, there's people who were on their high school robotics team, or they're doing this on a project team, and I've never even touched a breadboard before. Like, how am I going to succeed in this class? So there's a lot going on here. Each dot in this graph represents a group of 3. So the final competition was in groups of 3 students. The x-axis is that group's average final grade in the class, so bigger is better. The y-axis is the rank in the final competition, so lower is better. Like number 1 means they won the competition. Blue dots, nobody in the group had any prior Arduino experience. Or sorry, blue dots, somebody in the group, at least one person in the group did have prior Arduino experience. Red dots, nobody did. Look at the lower right corner of the graph, right? There's a couple blues in there, but like largely dominated by groups with no prior Arduino experience. And if you look up here, some of the people who actually did the worst did have prior Arduino experience. So I don't want to flip that anxiety and make you think like if you do have experience, you're now doomed somehow, right? But the point is there isn't just some clear bifurcation here where the class split and people who had prior robotics or Arduino experience had some huge advantage over people who didn't, okay? And that the coding stuff is going to be kind of different from what most of you have seen before, and we're going to try and get everybody kind of on the same page. And excuse me for 1 second as I mute my mic so I don't blow my nose into all of your ears. Okay, so again, that's kind of the whole, like, if you were nervous about this class for whatever reason, we're going to try and ratchet that down. Switching to the more boring logistics stuff, okay? I could not pick my favorite "it's in the syllabus" meme, so I just took a screenshot of all of them. I am not going to stand here and read the syllabus to you, but I will kind of go over some of the major things that I want you to know and kind of address my philosophy about this. One, for deadlines and extensions. I realize that as students, it is probably really annoying to at any given time be taking 4 different classes that all have different policies on attendance and extensions and drops and slip days and all of that stuff. As an instructor, I wish it was more standardized. It would be easier for me if the department just told me, this is the policy, use that. But every class is different numbers of assignments, instructors have different preferences, all of that stuff. So this class is modeled hopefully to be very similar in other MAE courses you have taken regarding slip days and all that stuff. Again, I'm not going to stand here and read the rules to you, but it's in the syllabus. My personal philosophy on this is also kind of that this is supposed to prepare you for the real world of having a job, right? And sometimes the real world has hard deadlines. Okay, if you want to go work for NASA or SpaceX, there is a launch date. You cannot show up a day late for that or forget. Okay, this class has a final robot competition. You cannot show up the day after the competition with your completed robot, right? Like, competition is over, you missed it. That being said, hopefully for intermediate non-critical deadlines, you get a job with some reasonable work-life flexibility, right? And I think, especially since the pandemic and kind of younger generations, like my generation and yours, have gotten a little better about this in terms of workplace expectations. But hey, I had a family emergency, can I get you that report tomorrow? Shouldn't be the end of the world. So that's kind of my approach here. Again, I very much live that, again, as a parent of 2 young children. Like, our 4-year-old was up in the middle of the night for some reason, and then there was a 2-hour delay this morning because it was so cold, so my wife and I were juggling childcare and getting to campus. Like, it happens, okay? You guys have different reasons than I do. And then that is all okay up to a point, right? It can't become a weekly recurring thing. So again, there's slip days and all that stuff in the syllabus, but you don't get more. Okay, it's not I used my 6 slip days, but I don't think this one should count. Can I have 7? Okay, don't ask. That's not how that works. Announcements. We all get too many emails. My experience is that if you post too many announcements, they just kind of become noise and people start to tune them out. So my plan is to reserve Canvas announcements, ideally for more important things, like, hey, I made a mistake in lecture, here's the correction. I forgot to mention this in lecture. Not homework 1 is posted, reminder homework 1 is due Friday, reminder homework 1 is due tonight, right? Because then I think people start kind of tuning it out. The caveat there is that I didn't know it was due is not an excuse. Okay, again, think of this as preparing you for the real world. You might get a job where your boss points at you in a meeting and tells you to do something verbally. That's it. They're not going to write it down for you. They're not going to send you an email. They're not going to put it in the calendar for you. There is no Canvas with deadlines, right? You just have to remember to do it. So I might announce something in lecture. That doesn't necessarily mean there's going to be an equivalent digital follow-up announcement for everything. Okay? This class does not have a single textbook because we are covering so many different topics. There are a ton of resources and videos on Canvas, kind of slide decks that sort of function as the textbook equivalent. And I made a lot of videos during the pandemic. So if you ever do miss a lecture, again, I'm not going to post an announcement that says, if you missed today's lecture, watch this video. But if you're all Cornell students, you can probably figure out today's lecture notes were about capacitors. I should probably watch the video about capacitors, right? I think you guys can make that connection. Ed discussion, again, this shouldn't be that different from other classes you have taken. The default is that all questions go on ed discussion. The exception is personal questions for me, right? So if it's about a SDS accommodation, concerns about your performance in the class, that sort of thing, for that, you email me, but you don't email the TA's homework help questions, right? That goes in either office hours or ed discussion, so it's public for everyone. You can be anonymous to each other. I understand sometimes people might be embarrassed about asking, and again, I guarantee you if you're confused, there's probably at least a dozen other people who are confused, so I should probably know about that. So in general, I'd encourage you not to worry about it. You can be anonymous to your peers, you cannot be anonymous to the instructors. And again, I think that is similar to the settings most other people use. Any logistics questions? Again, all of that is in the syllabus. I don't even have it all memorized, so I would have to go look up some of it myself, but that should all be on campus. Okay? Yes?
What are lab reports due with respect to the labs that they were done during?
We don't have lab reports anymore. So sorry, the question, if you can hear in the back, is when are lab reports due? At least for next week, there is no lab report. It's more kind of a data sheet that the TAs check off as you go through the lab. I guess since you asked that question, this is a good time to mention preemptively. I mentioned the individual kits. You will be using those on homework assignments. And I think sometimes people grumble about the length of the homework assignments in this class. I don't know if you've heard rumors of this from previous students, but the total workload has decreased in other areas. So this class used to have 6 labs with lab reports and 3 exams. It is now down to 4 labs, no lab reports, and only 1 exam. But some of those previous labs that used to be done in a group where only one person would use the oscilloscope have now been shifted to the homework. So the net workload is intended to be the same, but if you approach the problem sets the same way you would approach a class that has weekly paper and pencil only problem sets, you're going to be in trouble. Like they're due at 11 p.m. on Friday, don't sit down at 6 p.m. on Friday to start them. Okay? There are only, I think, 6 homeworks total throughout the semester, so they'll usually be, the first one is an exception, it's all paper and pencil, it's only out for a week, that should be much faster. But most of the other problem sets are going to be out for a period of either 2 or 3 weeks. Kind of think of them as like a little mini lab you're doing yourself. So again, start ahead, don't wait until Friday night to start them, and if you start thinking, wow, this is really long and miserable, remember that there are fewer labs and no lab reports. Okay, so the idea is to kind of balance out the net workload. All right. Immediate to-do list. Again, I'm not usually going to devote a ton of lecture time to kind of going over logistics stuff since these are only 50-minute lectures. But there are a lot of moving things all at once when this class starts. So I am kind of, excuse me, going to go over the immediate kind of this week list of things to do. There is a multiple choice concept test on Canvas that is due tomorrow night. This is really intended to help me see what you all actually remember from physics. Okay, because it's one thing to say, oh, the prerequisite class should cover this material. It's a different thing to see what people actually retain a semester or a year later. This is only graded on completion. Okay, so there is an I don't know option for every question. Please be honest, and if you either don't remember or have just never seen a topic before, go ahead and click I don't know. It kind of changes where maybe, I think it's about 30 questions. The first half are things you in theory should remember from physics, and the second half is stuff we're going to cover in this course that is not covered in Physics 2213 or whatever the number is. But again, maybe some people have seen in other places. And again, don't panic. It shows up as a graded quiz on Canvas because that allows me to see what percentage of people got each question right. But the TAs will then just manually go in and override the grading, give you full credit just for doing it. Okay, so again, it kind of helps me calibrate the first week or so of the course based on what people know. So please take that seriously. Again, if you don't know, go ahead and mark I don't know. Office hours, I have not scheduled those yet. There is a poll under the administrative section on Canvas to try and figure out what times work best for the most students possible. Again, this is not a guarantee. My experience in the past is that many, I am getting my kids in bed and then going to bed at 9 p.m. myself, but many of the undergrads and TAs are night owls anyway, so sometimes they're happy to hold office hours from like 10 to midnight or something. We will also, there are only 4 labs, and the non-lab weeks we will be using these scheduled lab sections as office hours. So even if the poll doesn't work out and you can't make the other ones, you should be able to at least make your scheduled lab section. I haven't scheduled mine yet. There is not another class in this room until 1, I think, so I will probably tend to just stick around immediately after lecture for questions. And then during lab weeks, that doesn't work well for people in the Monday, Wednesday, Friday first lab section because you have to run over to lab, so we'll kind of figure out how that works. Again, that poll is on Canvas. I will probably look at it on Friday and have the TAs schedule office hours based on that. There is no lab this week. Lab 1 starts next week. We do them in full weeks so it doesn't mess up the Monday through Friday section schedule. There is a pre-lab assignment that you will submit on Canvas. Go read the instructions. If you're confused about something, ask in a discussion. I'm not going to stand here and read all of that here. What I want you to do before class Friday, I mentioned Tinkercad, is create a Tinkercad account. Instructions for doing this are on Canvas. You should create the account with your Cornell Google login because we're going to, and I see people taking pictures. I am going to post these slides on Canvas after lecture, but obviously if you want to take a picture now, go for it. We will be using these. There's a feature called Tinkercad Classrooms that kind of lets you break up into lab sections for the pre-lab assignments. I would like you to have this account created before walking the lecture on Friday so we're not wasting the first 5 minutes of class with people creating an account for the first time. And bring a laptop to class on Friday. So this is one of the requirements for this class. If you don't have one, the library has both short and long-term loaner laptops. So I will let you know in advance when you're going to need one. I'm not going to do like a surprise, everybody get your laptops out, in case that's not something you usually carry around. This Friday will be the only time early in the semester we do it, because we're kind of getting ready for Lab 1 and learning how to use a breadboard. And then later in the semester, when we get more heavily into the coding component, it'll probably be a few weeks straight. Excuse me. I have had people try to use Tinkercad on tablets before. If you have a tablet with a keypad or something, with mixed results. So if you do have an iPad that you want to take notes on or something, I would recommend trying it out first. I definitely would not try on a phone. Your screen's going to be way too small to kind of do this. I mean, your vision might be better than mine at this point, but even then I think a screen is not really enough real estate to build a circuit and type code. Okay? And then we're going to be using, I don't think this is posted yet. The TAs are still sorting out the Tinkercad classroom thing, but that will be ready to go for lab next week for you to submit a pre-lab. And finally, homework 1 is posted. I'm not going to post multiple reminders that it's posted and about the due date and everything. That is due, I think, in the middle of next week. And this, as opposed to the multiple choice concept test, which is kind of conceptual stuff without calculations, this is really basic Ohm's law type stuff that you should remember from physics. But if you don't, again, no shame. That's what office hours and ed discussion are for, so go ahead and ask. That is graded for correctness, though. It's not kind of credit just for doing it like the concept test is. Logistics questions. Again, that is not necessarily an exhaustive list, but it's kind of the, excuse me, some of the major stuff at the beginning here. Good? Okay, now for the fun part, the robot competition. So I have some videos of competitions from a prior year, and this is kind of, you'll see in a second, this is kind of an overhead camera looking down on 3 different matches. And I want you to just kind of start thinking today about this competition at the end of the semester, right? Like, even if you don't know how you're going to do it yet, you can start thinking about the mechanical design and strategy for your robot, and then kind of circle back to whatever you wind up writing down today. But first, I want you to just kind of look at these matches and write down things you notice go wrong. I'll explain kind of the objective as we get into the first video here. So we have a board with a black border and 2 sides, a yellow side and a blue side, a bunch of cubes scattered in the middle. The color of the cubes does not matter, okay? The cubes can just be randomly colored. The objective in a 1-minute period is to push as many of the cubes as possible to the opponent's side of the board, okay, with limited sensor information. So there are no cameras and computer vision here. The robots do not have kind of a complete map of exactly where every cube is and where the other robot is. They basically have sensors that can detect the line to help them avoid driving off the edge, and they have sensors that can detect what color they're on. They can optionally use an ultrasonic sensors, using sonar like a bat to look out in front of them and detect the other robot. But that's pretty much it. Again, no cameras, no kind of really advanced computation. The robots also have to start. They have to start within I believe it's an 8 by 8 inch cube, but can then deploy up to a 18-inch diameter cylinder. So you'll see a lot of robots kind of have arms that deploy or something at the beginning to try and sweep more cubes. So just kind of, again, given what I've told you so far, you don't need to know all the details about how everything works, but kind of what you know about the objective and what the robots have available to them. Anything you saw go wrong in this first match. Adding insult to injury there. Okay, so there was one. Here's another one, 2 different robots with kind of 2 different mechanical designs. You see this one kind of drops this little bucket thing behind it to drive around and try and gather the cubes. This one is more of kind of a, I think that literally might just be a piece of construction paper taped to the front, kind of using as a snowplow. And I guess I should have clarified, every team gets the same kind of base kit to build your robot. So the chassis, the Arduino, the wheels and motors, the battery pack, and then you get a budget for additional fabrication of parts on top of that. It was $40 in 2021. I don't know if that has gone up with inflation. I need to check with the lab staff, but for things like laser cutting, wood or acrylic, or additional parts you want to order from McMaster, additional motors, that kind of thing. So not a huge budget. We can't blow thousands of dollars on each robot, and there's usually about 50 robots in the competition. But enough to kind of make each robot unique. Okay, so there was another match. Here is the third match, and I don't remember if this is the championship match, but the team on the left here ultimately won the competition because they figured something out. In order to win, you don't need to get all of the cubes to the other side, you just need to get the majority of the cubes to the other side. So they just built a heavy robot that deployed 2 big arms, drove forward a foot, and stopped. And they really pissed everyone else off because this was an incredibly simple design, but it worked really well. And there were a lot of, and look, this other robot is just sort of helplessly flailing around, but this one's too heavy, they can't push it or move these cubes. There were a lot of teams that actually got kind of angry because they spent a lot of time on a more complicated design that didn't work well, right? So just because something is complicated and you spend a lot of time on it, doesn't necessarily mean it's gonna win, right? There was a, one of the really cool ones I remember, there was a team that built a mechanism to spool out black tape to try and spoof the border and trick the other robot into not driving over the tape. Awesome idea, but like the mechanism was too complicated and it just on game day it didn't work that well, right? So that team was really mad that they just lost to the heavy robot that did nothing. So cool, but we kind of wanted to close that loophole. So after doing a couple years of pushing all the cubes to the other side, we switched it to having the goal to bring all the cubes back to your side. So you at least kind of had to do something to grab them or like drive over and turn around, and you couldn't just drive forward. We have done that for a few years now, and we want to switch things up again. So this year, the goal is going to be for your robot to gather the cubes, but it doesn't matter what side they end up on. Okay, so make sure that's clear. You do not have to pick them up. The cubes can still be touching the board, but they need to be touching your robot. So kind of imagine the outer perimeter of whatever your robot is. The cubes need to be inside that perimeter. Whichever robot has gathered the most cubes at the end of 1 minute wins. okay? So, what I want you to, we have a little under 10 minutes left. What I kind of want you to do with the remaining time you have, start thinking about how you're going to do that, okay? Given what I've told you again about the rough budget and fabrication, you'll have access to the RPL. What would the mechanical design for the robot be like? What would your algorithm be? Do you sweep around the edge? Do you dive straight to the middle? Do you avoid the other robot? Try to crash into the other robot?